So welcome to today's lecture about an introduction into deep learning and neural networks. And first of all, I want to start to tell you what deep learning is and what neural networks are, because there's a difference between them. And so we read a lot about artificial intelligence, and artificial intelligence, AI, is a huge diverse field where computers try to mimic human intelligence. And machine learning is one part of artificial intelligence where programs learn from experience. And this experience is provided, for example, by the training data. So machine learning has many different methods, and deep learning is one of them. And there's a difference between neural networks and deep learning. So neural networks are a biologically inspired approach to infer models from input-output relations, and these models can then apply to new inputs to determine the output. And deep learning is the set of techniques to learn in neural networks. Of course, deep learning can also be used besides outside neural networks, but mostly it's used in neural networks and also called hierarchical learning. And I want to show you some nice applications where you can use deep learning and neural networks. And here I think you already saw this example. Here we annotated, manually labeled some grapevine berries in images, and then we learned a model how these berries look like, and then we applied the model to new images, because once you learn how grapevine berries look like and you apply it to new images, you can detect them, count them, and once you count them and have the size, you can determine the yield from it. And what you can see here is an example for instance segmentation. So each berry is individually labeled, and then once you learn the model, it's applied to a new image, and in the new image each single berry is detected, and so you also can distinguish between different berries next to each other, although they are in the image neighbored. Another very nice example is maybe you already heard about the website "This person does not exist." When you go to this website, you see images of persons which do not exist in real life, but they are real-looking persons. And these images were generated by so-called generative adversarial networks. So here the network learns in a really nice way how images will look like, and the network trains itself as long as it cannot distinguish between real persons and fake persons. And a colleague of mine also applied this method to sentinel images. So here what you can see are two sets of images. Sentinel-2 images, that means multispectral satellite images, and one of the set is fake and one set is real. And you can now guess what is the set with the real images and the set with the fake images. And so the set on the left side are image patches from a data set Big EarthNet, and Big EarthNet is a huge database, benchmark database with nearly 600,000 Sentinel-2 images, which are annotated with different classes, which can be used for image categorization. And on the right side on the slide, you can see actual fake images, which were generated by a generative adversarial network. And this is work from Thomas Langer, and he programmed it and for example, to provide sentinel images, which can be used as additional training data later for a neural network. But we would talk about specific approaches more in this lecture. So, but now, after you know what you can do with neural networks and what is the difference between deep learning neural networks, let's have a deeper look into it. So here I illustrated a very simple neural network, and what you can see are circuits, and all these circuits are neurons. And you have here one input layer, one hidden layer, and an output layer. I always in my lectures color the input layer with red and the hidden layer with green and the output layer with blue. So you always know which neurons I am referring to. And what you can think of neurons are, so in the input layer, this is nothing else than numbers, your observations, or anything you want to feed as input to the neural network. And in the hidden layer and the output layer, you can think of a neuron as a function, which outcome is a number stored in the neuron. And this outcome is a so-called activation. And of course, you can have more than one hidden layer. And if you have multiple hidden layers, this is called deep. So the more hidden layers you have, the deeper the network is. So you start feeding your input, then the input goes through the hidden layers. In the hidden layers, you learn a new representation of your data, and then something is done with this representation. For example, if you want to do a regression, you implement a function into this neural network that you get a regression output. If you want to do classification, you implement another function which gives you a classification output. So you can see a neural network as some kind of representation learning algorithm, and then in the very last layer, the output layer, you decide what you want to do. And to summarize it, so the input layer is just the observational data. It's not restricted to some measurements or some observation. You can input whatever you want, and which can be, of course, read from the computer. In the hidden layers, you learn the new representation of your data. So remember the example I showed you in the last lectures, where you needed to calculate an output, and you changed from the one representation with the Roman numerical numbers to another representation, for which is much more easier for you to calculate with. And this is actually the representation learning which is done in the hidden layers. In the output layer, of course, this depends on what you want to do, which task you want to solve, and the output layer contains, for example, the class labels or estimations, or whatever is suitable for your task. So the simplest neural network you can think of is the so-called Perceptron. Neural networks is not a new idea. It goes back to the 50s or even before, but this is one of the first neural networks, and it was developed by Frank Rosenblatt, and it's called Perceptron. And this neural network contains of a summed weight of the inputs, and then this summed weight is transformed to an output. This very easy neural network has several binary inputs, so you only have plus or minus, or 0 and 1, and you have one binary output. Today, of course, there are better neurons and better neural networks, but we will talk about this later. So here illustrated is this simple perceptron. What you have is x1, x2, x3. These are your inputs. You have one neuron in the hidden layer, and you have one output, y tilde. And then what you do is you sum, or you have a weighted sum of the inputs. The weights are W1, W2, and W3. And you can think of that every time you connect two neurons with each other, there's one weight. And in this case, you have an output which is 0 or 1. That means it's a binary output. And next to the output, you can see the equations for the weighted sum. And in the end, you can use the perceptron to apply a threshold to make a decision. So this perceptron can be used for decision making, and depending on how you weight the input, a different decision you will get. And let's think of a very simple example. Imagine you want to decide, should I take this course? And because we have 3 inputs, you can, for example, think of, is the course mandatory? Does your friend take the course? So, because if your friend takes a course, maybe it's a good reason for you also to take the course. And am I interested in the topic? Should also be very important for this. And as I said, let's imagine for now, for the perceptron, you have a binary input. That means you have a yes, no. So you say, is the course mandatory, yes or no? If it's yes, it's 1. If it's no, it's a 0. Then you decide about weights. These weights can differ, of course, what is more important for you. And let's assume for now that W1 is 6, W2 is 2, and W3 is also 2. If you now apply a threshold of 5, so you set for yourself a personal threshold, if it's 5, and you go through and calculate the output, you will realize that with this setting, it only counts if the course is mandatory. Maybe it's not that important for you, and you decide, I don't care if it's not mandatory. I want to participate anyway, or because my friend participates, I also want to participate. You can decide on other weights, and for example, or another threshold. And for example, if you decide on a threshold of 3, also the other inputs count. And this is the whole example of neural networks. So you have inputs, you apply weights to these inputs, and not only that you apply weights to this input, it's also that you extract patterns and extract a representation from the input data, and then you apply weights to this representation, and then you apply some decision making process. You decide on a decision making process, and in the end you get a decision based on all what you have chosen. But you can imagine this is not powerful enough. You have only binary inputs, and also all what you have showed you is just a sum. It's a sum of a weighted sum of the inputs, so it's linear. You can do much more powerful things. For example, you can use not only binary input and output, but arbitrary continuous observations. You can decide on nonlinear activations in neurons, and there are specific ones which turned out to be really good to work in neural networks. And you can decide on the number of layers. So I showed you so far only an illustration with 2 hidden layers, but nowadays common neural networks have up to several hundred layers, and they work quite well. So let's have a closer look at the neural network architecture. So what you can see here is again 3 input neurons and 1 output neuron, and in between you have 2 hidden layers, and in each hidden layer there are 4 neurons. A neural network is nothing else than a complex mathematical function between your input and your output. So oftentimes a neural network is termed as black box, but this is actually not really the case, because as soon as you have access to the elements and the components of a neural network, you can write it down as a mathematical function. And this mathematical function can be seen under the illustration. So you have an output, and the output is a function of x, which are the input, and w are a vector of all the weights which are used in the neural network. So every time you have a connection between two neurons, there's a weight assigned. And if you write it down in a more detailed way, you can see that you have a nested function. So for example, this matrix W0 contains all the weights which are assigned to the very first hidden layer. So this vector, or this matrix of weights, is multiplied with the input, and this metric contains all the connections between each neuron, so each input neuron and each neuron in the first hidden layer. And here you apply a transformation, a nonlinear transformation indicated with F0, and when you have applied it, you have a new representation of your data. But of course, you want to have it more complex and more deep. What you do is you add another hidden layer. If you have a look at the function, you see that in the layer you have again weights indicated with W1, and all these weights collected in W1 are assigned to the second hidden layer, and this is then multiplied with this new representation in the first hidden layer, and so on and so on. So of course here you can also apply a nonlinear function, and you can continue as you want, and make the network deeper by adding just more hidden layers. And what I did not show so far is the bias. So remember when I was talking about linear regression, it's not only that you need the parameters for the direction of the linear regression line, but also a bias, which is some kind of shift. So it's intercept with the y-axis, and in this case it has a similar function. So it can be seen as a shift in the data and in the representation, and you apply this neuron, which contains nothing else than a 1. You add it to each layer, and then you do not have only a weighted linear combination, or a weighted combination of all your inputs or your representations, but also you have a bias. That means some kind of shift in your data. And what is also important is the loss function. So what you can see here is a y tilde. Y tilde is the estimated output. But all the weights which are contained in the neural network need to be trained. And they need to be trained in a way that you get the output you want to have. And in order to learn all the weights and adapt them in a way that you get exactly what you want as output, you need the loss function. And the loss function is nothing else than the comparison of your estimation and what is actually the true value or your reference data. This is what I told you in the first lecture. You can go back and have a look at this video if you want to see again why you need a loss function. And what you need to make your network very powerful are nonlinear activation functions. These were the function f I showed you on the last slide, and you have different possibilities for these functions, and some are quite good, some are but some are better. The most commonly used activation functions are sigmoid, tanh, and the rectified linear unit. So actually over the last years in development in neural networks, the activation function changed a bit. So in the early beginning, a lot of researchers were using sigmoid functions, but now more and more these ReLU functions are used. I will tell a lot more about it in the next lecture. But for now, what you need to know is you need nonlinear activation functions. You apply them in each of the hidden layers and also in the output layer. And depending which activation functions you do, your representation has different different characteristics. For example, the sigmoid activation function is necessary when you do classification, and you need to use it in the very last layer. So if you have more than two classes, you need not the sigmoid function, but the multi-class version of it, which is the softmax function. So softmax functions turn the output in the very last layer into values between 0 and 1. And this is exactly what you need for classification, because you want to have, you want to make statements about how probable is your class, or what is the score for a specific class. If you want to perform regression, for example, it would not be a good idea to use a sigmoid or a tanh function, because your output will be squashed to a specific value, and you could not model output values which are larger than 1, for example. So always think about what you want to achieve with your network, what your output should be, and what characteristics you want to use in your neural network. And I want to show you a very nice example of a neural network, and this is I took this example from Brendan Rohrer, and here you can see the reference on the slide. I show it very quickly because I like the example to show you how a neural network works. If you want to go into more detail, want to see more details and explain it step by step, just have a look at this video. So in this example, you want to decide if a 4-pixel image has a solid structure, a vertical structure, diagonal or horizontal structure. So imagine you have just 4 pixel values, gray values, and you have these 4 classes, and you want to classify this input into one of these 4 classes. So the task you need to solve is classify this 4-pixel image into the 4 classes. And for now, let's assume that the network architecture is given and also the weights are given or learned. Just imagine I'm an oracle, and I can tell you what the perfect architecture for it is and what the best weights are for it. Of course, we will come later in the lecture to the point where you need to learn the weights, or where I will show you where to start when you want to learn the weights. So here you can see the chosen network architecture, and the input is the 4-pixel image, and 1 pixel in this image is 1 input neuron. That's why you have 4 input neurons, and you have 3 hidden layers, and in each layer, or in the first 2 hidden layers, you have 4 neurons each, and the 3rd hidden layer you have 8 neurons. Because you want to have you want to decide between 4 classes, you have 4 output neurons, and each neuron is assigned to 1 class. And you can see for now that each of the neurons between two layers are connected, but this does not necessarily be the case. This is, for example, not the case if you assign a weight of 0, then it's like when you have no connection between these 2 neurons. Now I do not tell you only the architecture, but I also tell you what are the best ways to achieve exactly the output you want to have. And let's for now assume that every time you see a white connection, this indicates a weight of 1, If you have a black connection, this indicates a negative weight, that means -1. If you cannot see a connection between two neurons, the weight is 0. And you can also see the activation function. The activation functions are illustrated in the neurons of the hidden layers. And in the first two hidden layers, there's a tan-H function. That means your input is squashed between -1 and 1. And in the third hidden layer, you can see ReLU function. The ReLU function just cuts off all negative values. So if you have a value which is larger than 0, the weight, the value is just kept as it is. And if it's negative, it's set to 0. And for now, what is also a very nice notion is the so-called receptive field. Receptive field indicates where the network looks at. And this can be seen exactly very good in the input layer, because you have four pixel values in your image, and one neuron is assigned to one pixel. So the receptive field for the very first input neuron, it's exactly, only this part of this 4-pixel image. So it doesn't matter how you change x2, x3, x4. So for this very first neuron, the receptive field is independent of the other values. Okay, so now let's have a look at the exact computations which are going on in this network when you have an input and how you come to your output. So let's assume for now you have an input, you have as input this horizontal structure. That means you have two black pixels, -1 and -1, and you have two white pixels, which is +1 and +1. And what you now do is you have a look at the weights and the neurons from the last layer and the values, that means the activations which are stored in these neurons, and then you multiply the activation with the weight and you sum them together, and then you apply this nonlinear transformation which you decided on. So for example, let's have a look at the first neuron in the upper one, in the first hidden layer. So what do you have there? You have -1 as the first input neuron, and you have a positive weight. That means you have -1 times +1, which is -1. And then you have also a connection with to the last input, which is +1, and assigned as a positive weight. That means you have +1 times +1, which is +1. And then you sum them together, so -1 and +1, which is 0. And then you have you apply a nonlinear transformation, which is in this case a tan-H function. So it stays 0. So you had 0, then you apply this nonlinear transformation, which is 0. If you would have a value outside a specific range, it will be squashed between -1 and 1. So in the end, you have a 0 for this neuron, and this is stored as an activation in the first neuron in the hidden layer. And you do exactly the same process throughout the whole network. So you have a look at the weights, and then you apply multiply the weights with the activation stored in neurons in the last layer, and you apply the transformation. And you can see that you have in the first hidden layer, you have a 0, a -1, and a -1. Exactly, you do the same here, but now you do not use the input values, you just use the activation stored in the first hidden layer. And you have again a 0, again a 0, and a -1. And in the last layer, the activation changes. So you do not have a sigmoid or tanh function. We used here tanh function, but you do not have this squashing function again. Now you apply a reload. That means you just cut off the negative values. So for the first, it's easy because you have input which is multiplied with the weights. You have just a 0, so it's easy to compute. Which might be important is, for example, this here. So the last neuron in the last hidden layer is a -1, and you apply a positive weight, so actually you have a -1. But because you apply a reload function, it's cut off and set to 0. So again, you have it as activation 0 stored in this neuron. And for the very last neuron, you have a 1. And what you can see, this is exactly the output you want to have. What is shown here is, boxes are the recepted field, and the recepted field, the black and the white, indicating here where a negative influence is taken in the recepted field, and where a positive influence is taken. So from the last slide, you saw that you have as output exactly, you have all a 0, but for the very last one, you have a +1, which tells you this can be classified as horizontal. Of course, you need to decide beforehand what you want to have as an output, and what indicates you that something is a specific, is the specific output you want to have. So for the last example, I was telling you how the architecture looks like, and also I gave you the weights. This is not the case. So normally you do not have this, and you need to determine the weights on your own. And for each task and each loss function, and also for the training data you have, you need to estimate your weights. When you determine the weights, of course, also the activations in the network changes. So what you have given are input. This is the input layer in the neurons, and the output. And the output is, for example, the target class labels or the target observations, depending on if you want to do classification or regression. And also given is the network architecture, but you can also search for a specific network architecture, but for the weight estimation, you need a given network architecture, because you need to know which weights to determine. So the task is now to determine the weights such that the estimated output is as close as possible to your target output. So what you need to do is you need to minimize the loss function. And most commonly used loss functions are the root mean squared error when you perform regression tasks, which is nothing else than the squared differences between your estimated output and your target output, and the sum of it. And for classification, it's the cross entropy loss. So the cross entropy loss is a multiplication of the targets, which is an identity vector where the position of a 1 indicates the assignment to the class, and the logarithm of the probabilities. And you multiply them and sum over all classes and over all samples, and in the end you get a value which is the cross entropy loss function value. And both of them you want to minimize when you solve your task. And let's have a specific look at how the loss function value will look like using the example I showed you before. So remember, we had, or imagine for now you have a reference, and the reference is the horizontal structure, and you have given the architecture, and you have given the weights. When you now input exactly a 4-pixel image which looks like the reference, you have a 0 loss function value, which is good, which is the best case you can achieve. So you have for the very first outputs, for the first 3 classes, you have 0, a 0 and a 0, and for horizontal you have a 1. And when you compute the loss function value, you will get a 0. If you have not a horizontal structure but a vertical structure, it will look different. You will have a high loss function value, because now what you want, what you estimate is a 0, 1, 0, 0, but your reference tells you it should be 0, 0, 0, 1. So these 2 vectors do not fit together, and so you get a high loss function value. Again, for the last example is when you have a vertical structure. Your reference is 0, 0, 0, 1, but what you get is 0, 0, 1, 0. So it doesn't fit. You get a high loss function value. And speaking of loss function value, I want to talk a bit more about the so-called loss landscape. You can see here a very nice illustration of such a loss landscape, and this is very, very different from most of the machine learning algorithms you have learned about before. For neural networks, this loss landscape is non-convex. What does it mean? This loss landscape, here illustrated in, actually for 2 parameters, gives you gives you the loss function value for all combinations of parameters. So you can think of it when you have all the parameters in your neural network and you set a specific weight, you get a specific loss function value. If you do it for all kind of combinations, you will get such a loss function value landscape, short loss landscape. So here you can see a loss landscape for 2 weights W1 and W2, for example. And what you can see here, it has a lot of local minima. One global optimum, which is hard to find because it's non-convex. It's easy when you have a convex loss landscape, because then you just, you can immediately see where to go. But it's hard to find when you have such a non-convex loss landscape. And let's have a deeper look into it and how you are able to find a good solution. Please note that for neural networks, it's mostly okay and enough to find a good local minimum. Mostly you are not able to find a good set of parameters which gives you, which is actually the global optimum, which is okay. There are a lot of local minima which are also good and which gives you a good result. So when we talk about this weight estimation again, your task is now to find the valley in a tractable way. And with valley, I means actually, the global optimum, or if you can, and if it's enough, a local optimum. And the challenge is, as I said before, the loss function is mostly not convex, and with mostly, I mean as soon as you go deep, it will not be convex. And the problem is now the analytical solution is too complex. Normal neural networks have a lot of weights. So I told you, every time you connect 2 neurons, you have a weight. And when you go deep, it grows very, very fast, and it happens very fast that you have a lot of weights. An analytical solution would be that you have the output is a function of the input, and then you have the analytical solution to solve for the best parameter set, as you learned it in school. You find a derivation and set it to 0, but this is normally just too complex, and you will not be able to do this. So, but what you can do is you can exploit the local slope and iteratively approach the valley. What does it mean? Every time you initialize the weights in your neural network, that means you are at one point in your loss landscape. You're somewhere, and you want to reach a valley, a point closer to the global optimum. And so when you look around this point, you get a slope, and you want to have the direction which points to do a better solution. So a better parameter set with a lower loss function value. So let's talk a little bit more about slope. And when we talk about slope, we talk about gradients. So what you can see here is such a very, very simple loss function landscape, which is in this case convex and very, very simple. So what you can see here is the error, and when you change the weight, of course you get a different error, and the error is the loss function value. So in one dimension, the slope is nothing else than the derivative of a function. So what you need for this is you need to think about the change in weight. So when you change the weight a little bit, it will also change the error. And when you combine both of it, so the change in weight and the change in error, you have the slope. In multi-dimension, you have the gradient. So it's just the gradient is nothing else than the collection of the slopes in each dimension. And with dimension, I mean coordinate direction. And the negative gradient is the direction of the steepest descent. So in this case, exactly, you want to go towards the optimum. So what you do is you want to change the weight exactly in a direction that it changed the error, and you want to change it exactly in a way that you reach the global optimum. Okay, but how do you get the slope? So how can you determine the gradient, and how do you come from a point where you are to the point where you want to be? You can do it numerically. So this is the naive way. You can do it, for example, by finite differences, but this is very, very expensive. So what you do with finite differences is you have your current parameters, and then you add a small value in a chosen dimension, and you see where you end up. So if you add a little bit in one dimension, and you see where it goes, and then so you evaluate where you are, and you evaluate in all directions around you. But remember what I said, this loss landscape can be very high dimensional. If you have 1 million parameters, you have a 1 million dimensional loss landscape. So you don't want to do that. It's very expensive. What is good is you can get the gradient analytically. So and the gradient is exactly what you need to update your parameters. So let's have a closer look into it and how you can compute the gradient analytically. The reason why you can do it is because the loss function depends on W. And so it's much more efficient, because when you have an analytical solution for the gradient, not for the whole thing, it's easy to compute. And also it's much more exact than finite differences. So again, let's come back to this illustration of change in weight and change in error. So the slope is defined in the following way, and this hopefully reminds you of partial derivatives. So so change in weight and change in error, and this is the slope, and if you have it for multi-dimensional, is the gradient. So once we know how to compute the gradients, it brings us to an algorithm which is very efficient to update your weights, and this is called gradient descent. I'm very sure you already heard about it. If not, I would tell you now the principle about it. So the equation you can see here, you have your parameter set W, and then the very last term in this equation is exactly the gradient. And the gradient, as I said before, is the slope in each direction. So it tells you how to update your weights to get better weights. And these better weights are closer to your optimum where you want to go. And this parameter, which is in front of the gradient, is exactly the step size. We will talk a lot more about the step size because this is a crucial hyperparameter in a neural network, and it's you need to choose it wisely to have an efficient update. So you do not want to wait weeks for your result, but also you want to have a stable optimization process. And this gradient descent is an iterative process, so you update your parameters step by step, not too much, but not too slow. And at some point you will reach a parameter set which gives you results which you're satisfied with and which solves your task in a good way. And because normally you have a lot of samples, training samples, researchers came up with so-called stochastic gradient descent. So it's not that you in each step, every time when you make the update, you use all samples. It's more that you only use a part of it. And when you only use a part of it, it's called stochastic gradient descent. The reason is when you make the update and every time you use all samples is, first of all, it takes long, and also it's the optimization process is only good if you do small steps, and every time you make an update you need to compute a new gradient. So it's not that you can compute a gradient and it will immediately bring you from the position you are at in the loss landscape to the global optimum. This is not the case. You need to evaluate it in a small area in your loss landscape, and then you need to compute a new gradient. So it's enough when you use only a part of the samples. You use it for updating it, and then you need choose other samples and so on, and then you make your way through the loss landscape. And this whole thing is called backpropagation. Backpropagation is nothing else than doing this gradient descent but in a very efficient way. So let's have a look at a very simple toy example explaining the backpropagation. So in this toy example, you have a very simple neural network, and this neural network contains of an input X and the output, which is here denoted by E. So in this case, E is also the error, so there's no fancy loss function involved in this toy example. It's just the output you get. Also what you have is the activation in the hidden layer and these two weights which are assigned to the connection between the neurons. These weights are trainable. That means if you change them, the output will change. And when you change the weights, also the activation will change. But the only thing which does not change in the network is the input, because it's given. So what you do as the very first step is you have a forward pass. A forward pass is you give an input and then you compute what the output is. For the forward pass is here the output E is computed as X times W1 times W2. And also in between the activation and the hidden layer is computed by X times W1. So now what you want to do is you want to minimize the error. So you want to reach an error of 0, and what you can do to achieve this is you can adjust the weights. And when you adjust the weights, you also change the activation. And to update your weights, you do a backward pass. A backward pass means that you start from your error and you go through the network back to the input. You compute the gradients, and after you computed all the gradients, you update your weights. So how is it done? So first of all, you think of how do I need to change the input before the last output neuron, that it gets better, because you want to minimize E. So what you need to think about is how when I change W2 a bit, how does it change my error? And this is exactly the gradient. The gradient information you need. This is the partial derivative, and if you take the partial derivative, it's X times W1. But also the error is not only influenced by W2, it's also the activation A. So when you change A little bit, it will also change the error. And when you take the partial derivative of it, you get W2. And also if you go back, you want to know, or you need to know how does your activation A changes when you change W1 a little bit. And this is exactly X. And so you have these two trainable weights, W1 and W2. So you know W1 will influence E and W2 will influence E. So when you change W1 a little bit, it will also change E a little bit. And when you take the partial derivative of it, you have X times W2. So now you have all the informations. You need to compute the gradients. And there's an interesting fact which makes exactly backpropagation very efficient, and this is so-called chaining. So when you bring all this information together, you will see, so when you want to know how will a change in W1 influence your error, E, you will see this is nothing else than a multiplication of two partial derivatives. And if you would have a longer neural network, you will see it's just a chain of partial derivatives. And this makes backpropagation very efficient, because it's just a multiplication of partial derivatives. And so now you have your equations and how to update W1 and W2. You can compute the gradients, and you compute it for the whole network, and then you apply the gradients, and then you can make a forward pass again with the updated weights. And to have a look now at the chaining in detail, what I already told you is you have here this very deep network, and with a lot of hidden layers. And so each hidden layer is nothing else than partial derivatives which are multiplied. And the only thing you need to keep in mind is this whole thing is only efficient if all functions can be computed analytically. So the gradient needs to be computed analytically. So that's why the activation function should be chosen in a way that the derivative can be computed analytically. And let's give you some examples how you can compute the partial derivatives for different kind of connections in the neural network. So the first thing is what I showed you. It's a linear weighted connection, and this is what we used in the example before. So if you have multiplication, so A2 is the result of A1 times W1. You take the partial derivative and which is nothing else than W1. This is also the case for sums. Sums are much more easier. So when you have a sum and you take the derivative, you get a 1. But also for more complex activation function, for example, sigmoid and ReLU. Sigmoid has a nice mathematical property that when you take the derivative, it's nothing else than the sigmoid function times 1 minus the sigmoid functions. And also for ReLU. So ReLU here you have the maximum of 0 and the actual value. And when you take the derivative, you have the signum function of this ReLU function. So these are commonly used activation function, and you can see you can use the partial derivative of it, and you chain them together, and voila, you have the gradient, and you can make an update on your weights. Very efficient. So this is what I told you. So you make a forward path in the network. So you compute the output given your input. You derive new representation of your data, and then you see how it works. If it's already the output you want to have, or if you need to adjust it. If you need to adjust it, you just take do the backward propagation, and then again you do the forward propagation, and so on. So it's an iterative process. So the general optimization steps you need to do is, I told you about the forward and the backward propagation. What you need to do in the early beginning, and this is an important step, and I will talk about it in the next lecture even more, is you need a good initialization. Initialization means where you are in the loss landscape. And of course, it's much better if you're already close to a point where you want to be instead of very far away, because this will influence how long the optimization process will take, and also how stable it will be. So different areas in the loss landscape might be have a different roughness and surface. So it would be good if you are somewhere where the optimization process can be efficient and fast. So some more comments on how to train a network. I will start in this lecture, but also I will tell a lot more in the next lectures. I already mentioned that not all training samples are used to do backpropagation in each step. The reason is that you have sometimes millions of training samples and you just want to make progress, but you do not want to have a slow progress. So because this is computationally too expensive, what you do is you use batches of samples, and this term batch size will follow you during every time you have something to do with neural networks, you will hear about batch size. And batch is nothing else than a division of the whole training set in different sets, the batches. And here, for example, you have 4 batches, and all 4 batches are your training data set. And I already illustrated here, it's good to try to divide the data set in equal batch sizes, or in equal sized batches. Otherwise, you might end up with a very tiny batch size, and the gradient let your current parameter weights jump to a position in the loss landscape where you do not want to be. This can happen as soon if you only have a few samples, and maybe there's an unfortunate constellation of samples which will bring you to a position in the loss landscape which is worse than before. So the batch size refers to the number of training samples of one iteration, and you need to distinguish between two terms, which is iteration and which is epoch. When you talk about how many runs you took to reach your result, it normally means epoch, and it's not referred to the iteration. So weights are updated in each iteration. So every time you compute gradients and update your weights, you performed one iteration. But much more interesting is the epoch. So an epoch indicates the number of passes through the entire training set the algorithm has completed. So every time you used the whole data set and to compute an update, this is one epoch. So if the batch size is the whole training set, it's called batch mode, and then the iteration and the epoch are equivalent. And otherwise, one epoch consists of many iterations. And to illustrate it, you can have a look at, I made this plot. So this is a typical plot you get for an optimization process for a neural network. So you plot the loss function value, and then you have the number of epochs. What is actually happening when you have a very, very close look, you have two epochs in t and t+1, but in between you made a lot of updates on the weights, and these are exactly the iterations. So sometimes they're reported, sometimes not. So normally when you use some optimization software or some libraries for programming, in the end you plot the epochs. And there are different modes. I already told you about the batch mode. So you divide your data set into different batches, but these batches can have a different size. If the batch size is equal to the size of the data set, then the iteration and the epoch number are equal. That means every time you make an update, you use all the data samples. This is okay if your data set is small and you do not have so many training samples. Mini batch mode is actually the procedure which is used most commonly. And here the batch size is smaller than the size of the data set, but it's not 1, it's larger than 1. And usually a number by which the total data set can be divided. So as I said, it's a good idea to have batch sizes which has the same size. And stochastic mode, this is exactly when you talk about stochastic gradient descent, means when the batch size is equal to 1. So therefore the gradient and the neural network parameters are updated after each sample. This makes the network very flexible, but it would jump around a lot. So in the loss landscape, you can even jump back to higher loss function values, but in the end you have a high flexibility, and the chance that you find a good optimum, even if it's a local one, is high. Yes, this is one possibility. So you want to have a high flexibility, but then the gradients are very noisy because the samples will differ from each other, and the gradients will also differ a lot from each other. So you would jump around a lot. If your batch size is too large, that means your gradients are nearly the same every time, but that makes the whole optimization process very rigid. So it would bring you a very without a lot of jumps to an optimum, but it might not be a good optimum. So you need to decide and make a compromise between the flexibility and stability. What works mostly in practice, and here I talk about from my experience, and that means from examples from remote sensing, classification, and regression. And that means not with millions of training samples, but as it is the case, for example, in many computer vision tasks. Here, a mini batch size of about 5 to 200 is normally good when you have several thousands of training samples. Also, yeah, I can only repeat it because it makes the process much more stable. If the batch size should be equal and add up to the number of the training data set, because once you found a good batch size, you should stick to it and not have a small batch which always brings you back to a batch intermediate result. And I want to talk a little bit more about this underfitting and overfitting. I already told you in the last lecture about it, and overfitting is a real problem for neural networks. The reason is that you normally have neural networks which have a lot of parameters, and if you do not have a lot of samples, the tendency that you overfit the network is quite high. Just to repeat it, in case you forgot it. So underfitting is if your model is not able to capture the characteristics of the data set. So it's, for example, when you have a linear regression model for cases where you actually a quite flexible model, like a higher order polynomial. And overfitting is when you adapt so much that you also adapt to the noise. So you also here you need to find a compromise between underfitting and overfitting. Underfitting is quite easy to see, because here you have a high training error. So it's just then when you train a model, you see your training error is high, and you cannot achieve a training error which is you are satisfied with. With overfitting, it's it's hard to capture it, because when you only look at the training error, you might get the impression that your model is quite good because it's able to adapt to your training data. But actually the model is not good because it cannot generalize well to new unseen data. So you can only see the overfitting effect when you apply your model to unseen data. And I just want to briefly repeat the supervised classification procedure I told you in the second lecture. And I told you there's a specific step you need to perform. So of course in the beginning you need to collect training data and extract relevant features for the neural networks. The neural network does this for you. But then you need a training step. And then I said, this is optional. The optional is the validation step, but now we need this step. And this validation step is exactly which helps you to prevent this overfitting effect. As for the classical machine learning procedure, you also have a testing step where you classify your testing data, and then in the end you need to do an evaluation. So let's have a look at what is a validation set. And here we start from the very beginning. So what you have given is normally you have a labeled data set and an unlabeled data set. And the unlabeled data set, you do not have information anyway. So it's just that you learn a model on the labeled data, and then you can apply it to the unlabeled data and do, for example, a qualitative evaluation. What you normally do is to learn a model and to evaluate it on also in a quantitative way is you divide the labeled data set into training and testing set. And the testing set is used for evaluation afterwards. You're never ever allowed to have a look at the testing set while you train your model. So just treat it as non-existent. Just take it and put it away and do not touch it when you train a model. So how can you now perform this validation? How do you prevent, or what helps you to prevent this overfitting effect? What you do is you invent a validation set. So you do it on your own. You take all the data you are allowed to take, which is the training set, and then you do again a splitting. You split it in a training set, which is used to train the model, and one set, which is the validation set, here indicated in yellow. And this validation set is, you can see it as a fake testing set, which you are allowed to use. And so what you do is you use the training set, train your model, and then you apply it to the validation set. And because it's treated like unseen data, you can immediately see if your model is overfitting or not. So if the validation error is close to the training error, it's a good sign. If the validation error is much higher than the training error, it's a sign that you're doing overfitting. And that's why when you deal with neural networks, it's always important that you have a look at the loss curves and the accuracy curves. So such kind of curves in this way or similar, you will see a lot in near future. What you can see here is you have two accuracy curves and two loss curves. And two because you have your training set and you have your independent validation set. And what you see here is a typical overfitting effect. So on the x-axis you have the number of epochs, and the important point during this optimization process is exactly this box, which is called elbow, because here is the so-called elbow effect. That means starting from there, if you do a further optimization, the gap between your curve belonging to the training data and the validation data, the gap is increasing. And if it increases much more, it means the overfitting is much more existent. So what you do is when you have a look at this, you decide on when does the optimization procedure overfit, and then you stop there. You just stop the training. And this stopping of the training is called early stopping. It might seem a very easy idea, but it's very efficient, because when you have a look at these curves, you exactly see until which epoch you can go and when the network is just overfitting and adapting too much to your training data. So a small gap means the model complexity might be or could be increased. So if you train a model and you reach your number of epochs and the gap is quite small, you can try to make the network much more complex. Maybe you can even get a better accuracy and a lower error. If you have a huge gap, this is a sign that the model is most likely overfitted. So the elbow area, this is exactly this black box here. You need to have a look for it and search for this elbow area because this is an indicator to stop the training. And because the good thing is when you split your training data, this evaluation with the validation set, you can do all the time, and after each epoch, even after each iteration, you can check, and as soon as you see the gap is getting too large, you stop the training. So this is quite nice. It's not only that you can do it afterwards, you can, it's called babysitting your optimization process. So you just have a look all the time at it. Yeah, so the validation set can be used also for hyperparameter tuning and finding a suitable training setup. The suitable training setup I showed you before, but also when you, for example, test different hyperparameters and you're not allowed to touch the test set, you can also use this, for example, to analyze different learning rates. So typical hyperparameters which influence the accuracy of the network a lot are generally the learning rate during the training. It's good that you try a few of them, different learning rates, and also the number of layers or the number of neurons, and also the batch size has an influence. So train the model with your training data, and then take the validation set and evaluate and see which hyperparameters are good for the training process. Okay, so I told you a bit about the training setup and how you can, what you can do in a neural network to change the training setup. But specifically, things you need to think about during the optimization process is, first of all, or not during the optimization process, before, is the activation function. So which activation function should be used in your network? The choice of the activation function will have an impact on how good your network can be optimized, and how good you can find a solution. Data pre-processing. So because you do not need to think about which features to extract, it doesn't mean you need to think about the pre-processing. Pre-processing includes, for example, normalization of your data. Also, initialization strategy. So how do you choose the initial weights, and also the loss function value, and how to evaluate, because it's easy to decide if you want to do a regression or a classification. But even for classification, there are different loss functions, and also for regression. For example, you can use an L2 norm or an L1 norm. So these are all things you need to think about. So with this, I want to sum up for today. What your take-home message from today should be is that neural networks are quite flexible and can be designed according to your task you want to solve. This is a huge opportunity, but also it can be quite challenging in how you design your network. What I showed you today in the example is a so-called feed-forward neural network. So you feed your input throughout the network and change the representation. It's also called vanilla network. That means vanilla always means some basic, basic network. And it's also sometimes called multi-layer perceptron, but it's better to call it feed-forward neural network, because perceptron is always a little bit related to this binary input and output. So better use feed-forward neural network. So with this, I thank you for your attention, and I hope you enjoyed the lecture, and I also hope that you will enjoy the next lecture. Thank you.